All right, so we talked about the law of sines and we had that ambiguous case, and the law of sines looked really nice, but solving some of the problems was a little trickier. The law of cosines is kind of going to be opposite. It's a little messier to look at the formula, but it's a lot nicer to use. Just like last time, we got one video showing where it comes from. This is really good practice for people who are going on further on into mathematics, but if you don't want to worry about tomorrow use problems, just today, you could move on to the next video maybe. I wouldn't recommend it though, but you can make your own judgment calls. Example 1. Use the Pythagorean theorem. That's actually really cool, by the way. We'll get into that more later. But the law of cosines is related. I don't want to spoil it. It's related. Use the Pythagorean theorem on triangle ABD. I'll give you a graph in a second. To derive the generalized Pythagorean theorem. So, Pythagorean theorem only works for right triangles. Right? A squared plus B squared equals C squared. The generalized Pythagorean theorem works on any triangle. All right, so let's look at something. All right, I'll give you this picture now that I promised. We're looking at a triangle in the first quadrant. We can make it wherever we want. And let's say this triangle looks like it goes here, and then it goes here. And normally we're looking at the triangle CAB. But then we're also going to look at this point D right here. That's B, that's C, that's A. Let's also look at this point D. Let's call this theta. So little side A is opposite big A, little side B is opposite B, and little side C is opposite C. So the instructions tell us to use the Pythagorean theorem on ABD, on this triangle right here. All right, this is a right triangle indeed. And we're going to see, what does this say about the other triangle? So let's look at the point A. This point A is some point XY. And we know some things about that. Okay? But let's get into things, shall we? So the Pythagorean theorem says a squared plus b squared equals c squared. So this squared plus this squared equals that squared. Well, what is this distance here? Well, the distance here is A. Well, no, sorry. This whole distance is X, right? This whole distance is X, but we only want this small distance, right? X is this whole distance. We only want the small distance, so it's going to be X minus A. This right here, we go X units to the right. Oh, but we don't want to look at the A part. We're only looking at this side. So Pythagorean theorem says X minus A squared plus, what is this side length? Well, this side length is just Y. Plus Y squared equals the hypotenuse squared. And the hypotenuse, again, is just C here. So let's simplify this a little bit. Okay. That's going to give us that, okay, if we FOIL this out, that'll be X squared minus 2XA, or 2AX, plus A squared, plus Y squared equals C squared. So this doesn't look very useful, but let's rewrite this point. This point is, in terms of X's and Y's, that's not very useful. Let's rewrite this point with other things, like thetas. So if we were on the unit circle, X would just be cosine of theta. If we were on the unit circle, y would just be sine of theta. But the radius isn't 1, the radius is b here. So you could do a little trig. It wouldn't take you long. You get the x coordinate is b cosine of theta, and the y coordinate is b sine of theta. And if we write x and y in this fashion, look at what happens with our Pythagorean theorem. So x is b cosine theta. Let's plug that in. What's y squared? Well, that's b sine of theta squared. And that equals c squared. All right, and now we're just gonna have to do a little simplifying. Don't worry, it's actually not that bad. Here, I'm just gonna, let's just copy it over to the next page. Like so, and let's keep simplifying. Square a monomial, this is gonna be b squared cosine squared of theta minus 2ab cosine of theta. It looks awful, but I promise it's gonna get better. Plus b squared sine squared of theta equals c squared. And now we want to simplify this. But look at these two terms right here. What if we factored out a b squared from those two terms? Let's move them next to each other. Let's move those terms next to each other. B squared sine squared of theta plus b squared cosine squared of theta. And let's flip the order of the other ones too. Plus a squared. October, stop eating paper. So hold on. This is like running. It's like I'm teaching kindergarten. Kindergarten with trig. Actually, I don't think they eat paper in kindergarten. I don't have a lot of experience with kindergartners. You let me know if kindergartners eat paper. Minus 2ab cosine of theta. All we're doing in this step is writing things in a different order. Right, the red underlined things got moved around, and then I switched the order of the other two terms too. Because now, this red underlined thing, we can factor out a b squared, and that gives us sine squared theta plus cosine squared of theta, which equals 1. So what we really get is we just get b squared plus a squared. Write that in a different order. A squared plus b squared minus this other thing. I called it the generalized Pythagorean theorem. Look at it. If we hide this red term, it's exactly Pythagorean theorem. So it's just Pythagorean theorem with an extra term. Instead of a squared plus b squared equals c squared, if it's not a right triangle, just add one little term in here, and you can use it on any triangle. This is the generalized Pythagorean theorem, and this is 1/3 of the law of cosines. All right, and it says if we look at this triangle right here, any triangle like that, here's a relationship between these three sides. We can't use a squared plus b squared equals c squared, and in fact, our b and c are switched, which is fine. We can call things whatever we want. But we can use a relationship as long as we introduce some stuff about the cosine of theta. All right, so that's kind of where it comes from. It's just the Pythagorean theorem, right? All we did was use the Pythagorean theorem on here with a little bit of trig to replace that x and that y. So this is one part of the law of cosines, and in fact, you can switch this around however you want. Here we have a squared and b squared. Well, if we want, we can do it like this too. Let's have a and c on the left, solve for b squared on the right. And if we do that, what matters, right, is that this a and b is the same as this a and b. All right. And this theta, this theta, notice that theta is the angle, theta is angle C here. So this right here, this is angle C in this case. So if we change around thetas, this is going to be minus 2AC times the cosine of an angle. And this is going to be angle B. So angle C is when you solve for C squared. Use angle B when you solve for B squared. And again, there's one more form for the law of cosines. You have B and C like this. And then it's going to be A for when we solve for A squared. So 3 forms, the law of cosines. And again, yeah, usually you're going to see a C written right there, but however you want to phrase it. I'm going to do it actually. Let's be consistent. That's the law of cosines. And it lets you find the solution to different kinds of triangles. All right. We'll use it and show how to actually use this in use it and show how to use it. Yeah, we're going to use this in the next video. All right.